Hi, my name's Chris Collison, and today we're going to talk about some frequently asked questions associated with the experiment to determine Avogadro's number. So let's jump straight into some of those questions. We'll start with some of the obvious ones that you'll use in your abstract. The first one being, what's the objective of this experiment, and then we'll go on to think about some of the techniques you're going to use and how you can actually improve the experiment and why we're doing certain things that we're doing. Okay, thanks for listening. We'll jump over to PowerPoint. So let's look at some of these key questions. And the first question, as I mentioned, is what's the goal of this experiment? And so simply the answer is we're going to determine Avogadro's number. And so of course the next question you're going to ask is, well, how are we going to measure that? Well, quite simply, we're going to measure the number of moles of hydrogen gas that we're going to collect in an inverted tube. And at the same time, and independently, we're going to measure the loss of copper of a copper wire. How are we going to measure the number of moles? So I mentioned number of moles of hydrogen in here. So how are we going to measure that number of moles? We're actually going to use our ideal gas equation. So PV equals nRT can be rearranged to form N equals PV over RT. And so that's how we calculate that number of moles. We're also going to use an equation because we're going to tie this all into the number of electrons that are generated in our reaction, or a number of electrons really that are moved from copper and into hydrogen ions. So we're basically losing electrons in the copper. That's an oxidation process, and we're gaining electrons as we go from H plus into hydrogen gas. So those electrons, and we can count those electrons because we can measure the charge, that's Q, that's equal to the current that passes. And current, by the way, is measured in amps, and 1 amp is equal to 1 coulomb that's passing in 1 second. So it's really a coulomb per second. So if we take coulombs per second and we multiply by seconds, by time, we're actually going to end up with a charge, and that's Q equals IT. So the missing copper, by the way, we're also going to measure the missing copper. So this is really, again, answering our question, how do we measure the number of moles? So we're going to measure the number of moles of the missing copper. We're measuring the number of moles of hydrogen gas, and we're going to compare it to the electrons that are generated, or the electrons that are moving through this reaction. So as I've mentioned, how much charge is taken up by the H plus in order to form the hydrogen gas, how much charge is given up by the copper in order to form copper 2 plus, and that's figured out, we know that, as I mentioned, by the charge being equal to the current times the time. How do we connect 1 mole of electrons to its measured charge? So, well, we've measured Q, that's the total charge that's passed through the reaction. But how do we connect that to number of moles? Well, in fact, Faraday's constant tells us the charge on 1 mole of electrons. Faraday's constant is also equal to the fundamental charge multiplied by Avogadro's number. So either way, we can connect 1 mole of electrons to the number of moles of hydrogen gas that's formed, or copper ions that are formed. So some other frequently asked questions, right? Why must we weigh the copper wire? Well, we've got to weigh the copper wire in order to know how much copper wire has been converted into ions that will now be part of the solution. So we lose that solid, so we can immediately return the copper to the balance to measure the mass that's been lost to solution, to those copper ions. Another question, why must the bare copper wire fit entirely into the tube? So here's our tube. If we have the copper wire underneath the tube, then all the bubbles that come off from this copper wire, okay, here's our liquid, okay, around it, here's our beaker. So all those bubbles will float up to the top of our inverted tube. If, by the way, some of that wire ends up being outside of the tube, okay, so if we have a copper wire that's hooked up to a crocodile clip over here, here's our crocodile clip, which we're going to use to connect to the copper wire. Well, that copper wire is still going to react in the acid. We're still going to get that redox reaction taking place, but some of those bubbles of hydrogen are going to be lost to the atmosphere. And the problem is then that we won't be able to collect that hydrogen. We won't know how much hydrogen has been truly formed in the reaction that we care about. What else? Why must we clean the copper wire with 6 molar hydrochloric acid? Okay, so this is 6 moles per liter hydrochloric acid. Why must we clean that copper wire? Well, there's probably going to be some debris on the surface of that copper wire, and we want to get rid of it before we measure the mass of the copper. Okay, so we really want to make sure in chemistry that we're working with samples that are as pure as possible before we start weighing them. Why must the copper wire be matted dry before weighing? So we've gone through our experiment, we've removed the copper wire from the acid, from the sulfuric acid. We don't want to be weighing the mass of the liquid that's left on top of the copper wire. So we need to get rid of that liquid before we measure the mass of the copper wire. Simple. Again, the answer to these questions is the same answer. We need to be working with a pure sample before we obtain its mass. Will the acid dissolve the copper? So will the acid dissolve the copper? We could say, well, we've got some HCl, we've got 6 molar HCl. We've also got sulfuric acid, right? H2SO4. Will those acids dissolve the copper? Go to your activity series, have a look at copper, and you'll find that copper is lower than hydrogen in the activity series, and so it's not going to dissolve in acid. It's one of those noble metals that will not dissolve in acid, apart from in nitric acid, but nitric acid will form a redox reaction with copper. So nitric acid is really the exception to the rule, but copper is a noble metal. It's not going to dissolve in acids. Next question, why must you keep your current constant? Okay, the simple answer is Q equals IT. If your current is varying, if your current is all over the place, then it's going to introduce major errors, right? If the current is varying and we can measure time accurately, okay, that's pretty easy. But if our current varies a lot, then the charge that we write down is going to be a significant error, and that's going to go directly to our measurement and determination of Avogadro's number. Think about that, explain it in your conclusions, explain it in your data analysis for this experiment. Do you care if the sulfuric acid does not go to the top of the tube? Here's our tube. Do we care if the sulfuric acid does not go to the top of that tube? We don't, as long as we measure really the difference in position, the difference in height between the levels of sulfuric acid before and after we finished running current through the copper, right? So here's our copper, all right, and we're going to have a crocodile clip on here. We're going to hook this up to our power supply. We don't need to know that sulfuric acid goes absolutely to the top. We have a way of calculating that. Go see the Excel video, part 1, and that'll tell you how to do that. Why must you measure the height of the liquid in the tube from the top surface of the liquid in the beaker to the bottom of the meniscus in the tube? So let me draw this again. Okay, here is our tube. Here is the liquid in here. These are the sides of the beaker. What we care about is this distance in here, the distance between the height of the liquid in the tube, and we care about the height of the liquid in the beaker. That's what we care about. Why? Because the pressure is associated with this height in here. It's this height, it's this differential height that we care about. That is the H in our rho GH equation, and that is equal to pressure. Go and see my video on pressure in liquids and you'll understand why. So these answers are associated with all the frequently asked questions associated with this lab. Write them down. Use these answers in your data analysis, in your conclusion sections for your lab report, and you will be very happy with the outcome. So thanks for listening. Hope the lab goes well. This is a fantastic experiment. Lots of things coming together. It's a wonderful freshman experience for you all. See you in lab. Thanks for listening.